Yeah, so I'll be talking about supports and idempotent splitting in categorical probability. This is a joint work with my collaborators, which is Tobias Fritz, Antonio Lorenzin, and as well as Paolo and Dario, who are also here at the conference. And conveniently, now the paper is on arXiv, so you can check out the details there as well. Okay. On the Zulip channel, I put the slide so you can see the references there. And I will start with a very quick review of Markov categories, but because we've seen them so many times, I will just go quickly, and if there's any questions, then you can also ask. Click. Yeah. Okay. So one of the main examples is the category of stochastic matrices, which we've seen in Sean's talk, but this is the normalized version. So this is the Markov category with stochastic matrices and matrix multiplication as composition. Then we also have the Markov category of Markov kernels. We call it stock, and where the objects are measurable spaces. And there are some other examples as well that we consider. So in particular, we are interested in Borel stock, where we restrict the objects to standard Borel spaces. So those would be discrete spaces, as well as spaces that are isomorphic to the unit interval. We will also consider this category of top stock, where we consider objects are topological spaces, and the morphisms between them are going to be also kernels, but continuous kernels, in the sense that this assignment of input to an output probability of some open set has to be lower semi-continuous. And set multi, this multi-valued maps we will not consider so much, but there's also an example where we can apply this theory that we will develop. We have, of course, these copying morphisms that we have seen in other talks. We have a deletion morphism in a Markov category with respect to which all morphisms are natural. And this gives us the definition of a Markov category. But I will move on now, and we'll, we have this definition of deterministic morphisms, which means that copying the output of a morphism is the same as applying the morphism to two copies of the input. And this gives us a subcategory that we denote by CDET. So in particular, in these examples that we saw, for the Borel stock, this gives us measurable maps. And for top stock, this would be just continuous maps between continuous spaces, topological spaces. Okay, so absolute continuity is a concept that we will need to describe support. So let us start with this concept. So what is absolute continuity? Let us consider these two distributions on the top, P and F. So one distribution is a coin on the first two outcomes, and then there is a third outcome that has zero probability. F is just a delta distribution on one outcome. And so in this case, we want to say that F is absolutely continuous with respect to P, because every property that holds with probability 1 according to P itself also holds with probability 1 according to F. So how do we describe this? Well, we have on the left-hand side, we have P almost sure equality of two functions, G and H. So in particular, you can think of G as the identity function and H as a function that is identity on first two elements of this set, and then could be actually arbitrary on the last one. So these are equal with probability 1. And so in this case, we find that they're also equal with probability 1 according to F. And this is how we somehow witness that F is absolutely continuous with respect to P. And this in fact will hold also for non-deterministic functions G and H. On the other hand, if we consider different distributions, so in particular the f has now changed, now we still have that g and h are equal with property 1, but it is no longer the case that they are equal with probability 1 according to f, right? So in this case, they would only be equal with probability 1/2. They are equal on the second element, but not on the third element. And so that's why in this case, we would say that, in fact, this absolute continuity relation does not hold. So f would not be absolutely continuous with respect to p. And so from these two examples, we now extract an abstract version of this absolute continuity for Markov categories, indeed in terms of this implication of almost sure equality. So this is what it looks like for two, in this case, states, P and F. We would say that F is absolutely continuous with respect to P if we have this implication that holds for all possible morphisms G and H in the category. And we could extend it also to additional parameter that this P and F can take. So this is an existing definition of absolute continuity from an older paper, but it turns out that there are some properties that are not particularly satisfactory about it. And so in this paper, we change it slightly and we allow these test morphisms G and H to have an additional input. So now they are somehow the most general test morphisms you could think of. And so in particular, what's nice about this new definition is, that it actually reduces to the old one in the case of basically all the examples of Markov categories we are interested in. And at the same time, it's also preserved by the tensor product just as a consequence of the definition. It has some additional properties. For example, it's preserved by post-composition under causality assumption, and it has this property that you can see fairly easily from the definition, which is that if F, the morphism F, factors across P, so if F is composed of P and another morphism before it, then it's necessarily the case that F is absolutely continuous with respect to P. And so this is good to keep in mind when we talk about supports. So now I will switch to support. So if there's any questions about this definition, then maybe it'd be good time. If not, I'll just continue to supports. Okay, so what is a support of a distribution? Let us consider this distribution P again. The support we think of as the smallest set of outcomes that occur with probability 1. So in this case, this would be just the set xy, and we have that x or y happens with probability 1. And in particular, we don't want it to be just a set, but actually a sub-object of x. So we've described it as a morphism, this SI morphism, which we call support inclusion. It includes xy into xyz. And a particular property that we can notice in this case is that if it is the case that we have another distribution f, or maybe even a morphism f, that satisfies this absolute continuity relation with respect to p, then in fact this f has to factor through this support inclusion. And this factoring will be also unique. We can slightly generalize this notion of support if we allow for additional input. So in this case, P would be a stochastic matrix instead of a distribution. And in this case, once again, we want to think of the support as the smallest set that occurs with probability 1, but now for every possible input. So in this example, this would be the set of x, y, and z, because that set happens with probability 1 for every possible input. And now if we move to other examples, we can consider the topological example. And in particular, we want to look at somehow nice topological spaces, and a subcategory of the Tikhonov spaces, which you can think of as all metric spaces, and in fact, all compact Hausdorff spaces satisfy this. In that case, the support we want to think of as the smallest now closed set of full measure. So this would be, again, some kind of sub-object of the space on which the measure is defined. And in the case of the measure theory, so in Bohrel-Stock, we want the support to be the smallest measurable subset. Now, the smallest measurable subset will not always exist. So in that case, we would just say that the support is not defined. The measure does not have a support. However, in both of the cases, if the support exists, then we once again have this property that any morphism that is absolutely continuous with respect to P will necessarily factor through this sub-object inclusion. And so now maybe you can kind of see where this is leading. We will use this factoring property as a definition of a support in a Markov category. So let's move to that. The categorical support categorical definition of a support is that if we have a morphism P in a Markov category, then the support is given by a deterministic subobject S of its codomain, and in particular an inclusion, the support inclusion, that's a monomorphism, which satisfies this universal property that every morphism that's absolutely continuous with respect to P will factor uniquely through the support inclusion. And in fact, this definition can be rephrased slightly, which may be useful for certain purposes. So there is an equivalent formulation of it as a representation of a particular functor. So in particular, it would be a natural isomorphism between the Homestead on the left and Homestead on the right, where we only restrict ourselves to morphisms that are in this absolute continuity relation to P. And in particular, we also require this natural bijection to restrict to deterministic morphisms. And in this way, we get that the inclusion itself is deterministic. So if we apply this now to our examples, we find that in Finstock, also for the multi-valued maps, and as well as the topological case, all morphisms have a support in this sense. And this somehow categorical notion of support coincides with the somehow natural notion of support in each of the examples. And likewise for the measurable case, but once again, there will be some morphisms in Bohrel-Stock that do not have a support. In particular, the non-atomic measures, such as the Lebesgue measure, will not have a support according to this definition. So this definition of the support is what we somehow propose, but it is not exactly the same as some ideas about supports in Markov categories that have been floating around in the past. So let's try to connect them. We also describe somehow a slightly stronger notion of a support, which is what we call split support. And so that would be a case when this support inclusion is in fact a split monomorphism. So it has a left inverse, which this SP morphism, which we call a support projection. So you can see that for the case of the stochastic matrices, every support inclusion will have a left inverse. And so in that case, all the supports are split. And in fact, this is also the case for more general measurable spaces in Bohrel-Stock, that all the supports that exist are in fact split in this sense. The nice thing about these split supports is that they are indeed also preserved by tensor products. As far as we can tell, the supports from previous slide are not, but we also don't have a counterexample for now. However, there is a slight kind of caveat, in the sense that there is actually a measure in Tickstock, so this is the topological case, which has a support. So it has a smallest closed set of full measure, but this support is not split in this sense. And so in this sense, we think that these split supports are maybe not always a necessary additional requirement, also because a lot of the theory can be actually derived without this support projection, without this additional assumption. One thing that you can notice about the split supports is, of course, that if you compose the projection followed by the inclusion, then you get a split idempotent on the outcome set of the morphism P. But it's not any split idempotent. It has additional properties, and we call it static idempotent. So what is this static idempotent? We now move to this discussing idempotents in Markov categories. So we can prove that any of these idempotents that comes from a support is static in the sense of the equation in the bottom right. But there are other versions of somehow structured idempotents in Markov categories. We define these three types. So there's the strong ones, balanced ones, and static ones. It's not so obvious from the definitions, but there is like an interpretation of the condition for the balanced idempotents that says that they satisfied what's called a detailed balance condition. The static ones you can think of as, if you think of them as an update map for a Markov process, then this condition says that the process stabilizes after one step, so in that sense it's static. And the strong one is in some sense like a strengthening of the balance condition. And you can see on the top kind of the Venn diagram of inclusions, of implications between these conditions. And in fact, already for stochastic matrices, we find that all the regions are populated. So all these notions of idempotence are distinct, apart from the general ones, because as we will see, all idempotents in Finstock are in fact balanced. So here are some examples. In Finstock, we have a strong idempotent which just takes two inputs and replaces them with a fair coin. So in this case, you can notice that if you split this idempotent, you get a projection which is deterministic. An example of a static idempotent is one that is identity on the set of its fixed points, and for the remaining point, it just produces a random element of the set of fixed points. And in this case, you can see that it is the inclusion of the splitting that's deterministic. And then there is also an example of a balanced idempotent that's neither static nor strong. And in this case, if you split it, you will find that neither the projection nor the inclusion are deterministic. And these facts are in fact more general. So we can show that in any positive Markov category, so that's a Markov category with an additional assumption, if you have a split idempotent, it will always be balanced. And we can characterize the strong and static ones by virtue of whether the projection or the inclusion is deterministic in this case. And so as a corollary, because we know that the categories, the examples that we considered are in fact positive Markov categories, in all of these, here I write idempotents. What I meant to write is that the split idempotents are balanced, but in fact, we have also another result which shows that all the idempotents in these categories are balanced, but it does not follow from this result. But now we want to use this fact that we can think of idempotents, in particular in Borel stock for the measurable, for the Markov kernels, as being balanced, we want to use it to, in fact, prove that they have to split. So this is what we do next. In particular, we have this theorem about Markov categories, which has several assumptions that I didn't have time to discuss today. So in particular, we have the positivity assumption. We have an assumption about representability. So if you were at Arip's talk, he talked a little bit about representable Markov categories. This is an assumption that we have these distribution objects. And at the same time, we also assume what's called, what we call equalizer principle, which is in some sense a weaker version of supports. So we know that Borel's stock does not have all supports, but we can show that it satisfies this weaker notion, satisfies the equalizer principle. And so given these three assumptions, we now show that an idempotent in this Markov category is balanced if and only if it is a split idempotent. And because we've already know that all idempotents in Borel stock are balanced, this gives us that every idempotent in Borel stock splits. And so as far as we know, this result is not known in measure theory, or is at least not, we didn't find it in the literature, but there is a very similar statement from the 40s in a paper by David Blackwell on idempotent Markov chains. And there he provides a kind of decomposition of idempotent Markov kernels, but this decomposition is not exactly a splitting. It follows from the splitting, but it's a bit weaker. Okay, so to summarize, in this work, we give a new definition of absolute continuity for Markov categories, which as a consequence is compatible with tensor products. We also provide a new definition of supports that recovers both the measure theoretic and topological notions. And finally, we define these three different types of structured idempotents in Markov categories, using which we then give a somehow categorical proof of splitting of idempotents for Borel stock. And this paper has quite a lot of details, which I was not able to talk about. I'll just leave them on a slide and maybe take some questions. Thank you.
Any questions either here or online? Yeah.
Thanks, really nice talk. Yeah, I was wondering if for the absolute continuity part, normally I think of that as meaning that there's a density for one with respect to the other, for a measure of one with respect to the other, right? Is there anything to say about how densities relate to your treatment of absolute continuity?
Yeah. So at the moment, in Markov categories, we don't have a Radon-Nikodym theorem. So we cannot specifically talk about densities. It's plausible that we would be able to kind of give a theory where we have densities, and then you would probably want it to be somehow related to the absolute continuity, but at the moment that's not the case. Yeah.
Thanks.
Any other questions?
Thanks. Okay. So for the, yeah, I tried to think about supports before at one point. I was, but don't know as much measure theory, and I looked into it, trying to think about if they're there in Borel's stock, and it seems like they're normally defined to be a closed set there, right? And were you saying that it's not just that it's the smallest measurable subset? It's like in general the support I thought was sort of this closed. There's a definition of it that's closed anyway, so it's you have to think about more than just the measurable sets. And you're basically saying that you do capture that, but only in this other subcategory of Borel stock, I can't remember, the Titch stock.
So Titch stock is actually not the subcategory of stock, because there we have the kernels are different. So the kernels are these continuous kernels, but there indeed somehow the subobjects necessarily are closed subsets. So there somehow the support is a different notion. Yeah, there you always have a support, because you can always somehow take you can always intersect somehow sets which have measure 1 and get the smallest one, and it's going to be close, but it's not necessarily going to be somehow, if you do it for these measurable sets, you will not necessarily get a measurable set.
Thanks.
Okay, thank you very much again for the talk.